back. There was apparently nothing to worry about. My imagination is overactive. Everyone is okay, and it's early morning, so you will hear animal sounds that are loud, which normally aren't. I just thought maybe something, not someone, is being hurt, but apparently not. All right. Now, yesterday, I sort of started the unigram tokenization page of this course, but yeah, I stopped at like just the discussion, the explanation of the algorithm. So I wouldn't say I got far. The only thing was, I was curious, why are we splitting like this? Like, based on what? So I hope there's an answer. If not, then that's fine. Yeah, okay. Because the algorithm is supposed to be the learning part. And I don't think there will be an explanation of the split, but let's see. So, tokenization algorithm. A unigram model is a type of language model that considers each token to be independent of the tokens before it. Right. It's the simplest language model. Yeah, and kind of my favorite. I really love it. In the sense that it's probably of token probability, that the probability of token X given the previous context is just probability of, really? Oh, because it's a unigram, duh. Then bigram and trigrams have more context in them. Okay. So if you have, if we used a unigram language model to generate text, we would always predict the most common token. Yes. Which, like, I will say it and I will say it again. I said it yesterday, I'll say it again. Most common token has, like, almost always has no zero information. What's wrong with me? Least common tokens always have more information, but then it might be just a one-off thing, so it's a whole thing. It's a whole thing. Probability of a given token is its frequency, the number of times we find it in the original corpus divided by the sum of all the frequencies of all tokens in the vocab, to make sure the probability sum up to 1. Yes. For instance, UG is present in hug, pug, and hugs. Wasn't there a bug? There was also a bug. So it has a frequency of 20 in the corpus. Yeah, so here are the frequencies of all the subwords. They sum up to 10. So probability of the subword UG is 20 divided by 210. I'm good. Thank you. I am not going to do anything. To tokenize a given word, we look at all the possible segmentations into tokens. All possible segmentations. Okay, that I understand. That makes sense to me. All right. Okay. Compute the probability of each according to the unigram model, since all tokens are considered independent. This probability is just the product of the probability of each token. For instance, tokenization of PUG has this probability. How many times P occurs divided by all possible letters, right? 210 has to be letters now. And then U and then G. and then we divide them. And if we check for PU and G, it's different because PU together has a different probability, I guess. And then with the G. So that one is more likely. Which one? Oh yeah, there are 3 zeros here. Oh. Why? Okay. In general, tokenizations with the least tokens possible will have the highest probability because... Huh? Wait a second. Tokenizations with the least tokens... Oh, shoot. Meaning if your corpus is smaller, not if the thing doesn't appear in your corpus, then it has the highest probability. That would make no sense. Yeah. All right. Which corresponds to what we want. Intuitively, we want our vocabulary to be smaller, I think. To split a word into least number of tokens possible. Ah, got it. So just don't split words then. Don't create subwords if that's your goal. I mean, I'm sure making subword is a plus, but you could just split on space. The tokenization of a word with the unigram model is then the tokenization with the highest probability. Really? So we just split by character and then recreate, and then based on probability we keep stuff? I don't know. Let's see. In the example of pug, there are probabilities. The probabilities probabilities of pug. These two are the same. This is different. We kill this, we keep one of those. Okay. I think subword is about generalization for handling words not seen during training. Good point. Absolutely good point. I'm just saying, if your goal is to have the highest probability, actual words are better, but your point stands where subwords are better in general, especially with the unseen stuff. Yeah. So yeah, pug would be tokenized as PUG or PUG, depending on which of those segmentations is encountered first. Note that in a large corpus, equality cases like this will be rare. All right. Okay, so I am getting the answer I wanted for the segmentation, so I'm happy about that. In this case, it was easy to find all possible segmentations and compute their probabilities, but in general, it's going to be a bit harder. There's a classic algorithm used called Viterbi. Wow. Me and my fascination with having good pronunciation. It's unhealthy. Someone tell me how to pronounce this. And why is likely the only thing that is purple? Oh, ooh, HMM. I love HMM. If I remember anything of it. Viterbi, thank you. Seems like ideally you'd want to train on words split into subwords and those same words tokenized as single token. It does take track of what's a split part of a word and what's a beginning of word. So I like that. So yeah. Okay. Viterbi, maybe. Yeah. There is no help with that pronunciation. Quintana. Okay. Essentially, Quintana is a Korean meme. Well, I think less of a Korean meme and more of a K-drama meme. Anyway, essentially we can build a graph to detect the possible segmentation of a given word by saying there's a branch from character A to character B. Okay. I like that. I actually like graphs. The tree style ones. If the subword from A to B is in the vocab and attribute to that branch, the probability of the subword, I can visualize it. We have a word like, I don't know, door. We'd have DOOR. Each of them have their own probabilities. And then you link D and O together, and then O and O together, and then O and R together, and those are, but no, I was like, doesn't that become a bigram? No, it doesn't. We're still within the confines of a word? I don't know. Anywho. To find the path in that graph that is going to have the best score, the Viterbi algorithm determines for each position in the word the segmentation with the best score that ends at that position. No, I did not understand what I read. For each position in the word, so meaning for each letter, the segmentation with the best score that ends at that position. Okay, so up to here, I think. I mean, we'd have to try and do all combinations, but hey, since we go from the beginning to the end, the best score can be found by looping through all subwords ending at the current position. For now, we're just saying from the beginning to now, and then using the best tokenization score from the position this subword begins at. Then we just have to unroll the path taken to arrive at the end. Okay. Let's take a look at an example using our vocabulary and the word unhug. That's a weird word to use as an example. For each position, the subword with the best score ending are the following. We have you, and then we have UN, which, okay, it's just going down. These two are similar. What? Hug is that small? That's surprising. So these are the positions of the character. We're not doing last time we did PU and G, which is a different combination of P and UG, but we're not doing that here. I don't know why. That's what? Unhug would be tokenized as UN and hug? Why? I don't get it. I mean, these are all similar, but who told you to choose this? This has... I don't get it. Hug gun? Why? It's supposed to be HuggingFace? Okay, back to training. Like, I understood this part, but then why did we split on UN and H? Back to training. Now that we have seen how the tokenization works, we can dive a little more deeply into the loss used during training. At any given stage, this loss is computed by tokenizing every word in the corpus using the current vocabulary and the unigram model determined by the frequencies of each token in the corpus. Okay. Tokenizing every word in the corpus. Okay, you're not telling us exactly how, so all right. Each word in the corpus has a score. Wait, isn't that supposed to just mean not hug? Like to unhug someone like that while you're hugging them and then you stop hugging them. That should be unhugging. No? Each word in the corpus has a score. Yes. And the loss is the negative log likelihood of these scores. That is the sum of all the words in the corpus, and then you negative log likelihood. Yeah, okay. So to go back to our example, okay, I couldn't get there out of context. Fair. It could mean something else, but I just went for the simplest. Yeah, there's a word for that. Is it Occam's razor? Anyway, simplest explanation. The tokenization of each word in their respective score is. Okay, so yeah, it splits on stuff and then it chooses whatever it feels is good. Cool. I don't know, like most of the unigrams I've seen are split on space. Maybe that's lazy. I like the word piece. It's word piece. No? Something like that. Okay. So yeah, loss is sum of all of them with their so we have hug, we have yep, all of them. We have so the actual loss is 169.8. Okay. Now we need to compute how removing each token affects the loss. This is rather tedious. So we'll just do it for 2 tokens here and save the whole process for when we have code to help us. In this extremely particular case, we have 2 equivalent tokenizations of the words, of all the words, really? As we saw earlier, for example, pug. Oh yeah, we could have PUG and then PU and then G. Got it. Thus, moving the PU token from the vocabulary will give the exact same loss. Why? Oh yeah, we removed PU because P and UG is the same thing. Got it. Okay. On the other hand, removing hug would have a huge loss, make the loss bigger. Because of tokenizations, hugs and hug will have a different score. Yes, their score. It will be raised by 23 points. Okay. So we can remove PU but not HUG. Hug. Got it. Implementing unigram. Now, let's implement everything we've seen so far in code, like with BPE and word piece. This is not an efficient implementation. It's just a concept. Quite the opposite. It should help us understand better. We will use the same corpus as before as an example. This is hurting my brain because I want to read it as before as, like as well as, but it doesn't work that way. I think something like Japanese won't tend to split on space, as word boundaries are often denoted by a change between character sets. I don't have enough information, but like based on just English. That's what I thought should happen, but yeah, sort of what I've seen as well. But yeah, Japanese, Chinese probably are those cases where you can't split on word. And also like Arabic can be an example because there's a lot of more meaning within a word if you split it than if you don't. Like there are spaces obviously, but things tend to be linked together that you could split them. But how? That is a question that I am not, I can't answer. So we are using XLNet base cased. Yeah. Split on every glyph. Ah. For Chinese? I don't know. Now I'm thinking, what about Korean? Because they also have space. From what I have heard, Chinese doesn't even use space, which is like the thing that is the odd thing out of the other languages. How much code is there? Because I am lazily thinking that I'm not gonna run it. Oh wow, that's a lot. I mean, I can always see the answer, but I guess it would be fun if I tried a different language. That wouldn't be fair, though, would it? Oh, Japanese doesn't use space. Ah, I did not know that. Have I not seen enough anime openings? What's wrong with me? Okay, here's the code. Oh, cool. Hi, I don't care as much as I should. I was thinking I'm gonna add a few examples of different languages. So, while you are installing, I'm gonna get different sentences. Has 3 character sets. Katakana, hiragana, and kanji is the only one I've heard. Part of word boundaries is switching between them, I think. Wow. People who speak languages with just difficulties within the language have big brains. I am not one of those people. So, examples. Let's go for Arabic. اللغة العربية. Wikipedia. You're not supposed to say Wikipedia because P doesn't exist in Arabic. Wikipedia. What should we do? Give me. That's اللغة العربية هي أكثر لغات سامية. Oh, true. Okay, let's take this much. I don't want to take the things. I don't want to take it. Too much information. Wait, اللغة العربية is a he means she, by the way. My brain stopped working because he is he in English. One more. We have an Arabic sentence. What? Well, doesn't matter. I didn't bring the subject of the word because it had all of these stuff. I can take you, but now I don't know where home is. Like, where is the start of the sentence? Akthar. Hopefully here. Yes, I did it. Okay, so we have one for Arabic. Let's try Korean. The language. Yes, thank you. And also please turn it into Korean because that's the whole point. Oh, oof. That's not something 한국어 or 조선말. 대한민국과 조선. 우이. I don't care. I mean, I care, but it's not something that I need to care about right now. Just Nur Turen. Both of them. Tsurun. Kina. I can't read. Help. Anyway, it's hard. I have a hard time reading Korean. It's not easy. Okay. There. Good. Did this. Now I feel evil, but in a good way. Should we go for Japanese as well? For the fun of it? Because let's try. I don't know why I'm searching for the language and then I'm doing the thing. I can just update this to be in Japanese. This has to be Japanese. Let's take something difficult. No, there are too many Chinese letters within the sentences. Can we find a purely... Oh, no, it's not. It's probably one of the things we were talking... Hi! Hi, dude, what's up? The issue with the whiskers is that it's on top of my glasses. It looks like it's on top of my glasses. Otherwise, thank you. Welcome. Trying to find... You know what? I'll just take whatever is here. You're probably right about the changing between the characters, because like this is the only one that I can recognize to be Japanese. Like otherwise I think it's Chinese, but that's probably not the case. Like these look like things I've seen in Ghibli movies. So Ghibli? Oh, I don't know. Anyway. There. Ooh, that's long. Is there a different... Is that supposed to be a dot? What is that? Huh. I don't think I'm gonna understand Japanese language today, but hey. Okay, so this is obviously trained on English, I'm thinking. So let's see it struggle. I'm probably supposed to be reading what's supposed to be doing. Okay. So, we begin by counting number of occurrences of each word in the corpus. Let's do that. So, was that supposed to be spaced? Akthar is 3 times, Lughat is 2 times, otherwise everything is 1. For Korean, we have Saiga, well, I don't know where that's coming from. And then you can see it did not split on Japanese at all. How cool is that? It was able to, I mean, badly, very badly, because you can see it's not splitting on dot. Wait, that makes... Are we putting it all together? The corpus? Isn't it a loop? Why are you putting it all together? Like there's Arabic plus Korean in here, and here you can see the English being here, and then the Korean being here. So that, oh, you can't see the English because it's behind my head, but it's right here, yeah. And then we have English. And for the splitting, so it takes the text, probably sees it as one thing. Okay. We need to initialize our vocab to something larger than the vocab size. Oh, how? Okay. We want at the end larger. Okay. We have to include all the basic characters. Otherwise, we won't be able to tokenize every word. But for the bigger substrings, we only keep the most common ones, so we sort them by frequency. Okay. We are splitting on whatever it feels like splitting on, which, yeah, we sort of saw that. Why can you not see my face? I'm right here. Okay. Oh, is that it? You're kidding. Oh, we're just looking at like top something, top 10. L is dominating this here. Alif and then L. Why do you have two different ways of writing L? Is this supposed to be like a space around it? I don't get it. Oh, got it. Got it. This is from start of sentence. This is technically middle of sentence, but that's not true because that's not how Arabic word works, right? Where is L within a sentence? I mean, within the word, boundary of a word. There. The only case, no, it doesn't exist. Just space. That's literally the only thing that's before the L. These are all the L's. Oh my God, it assumes this is L, which is not. It is not. Oh, that's a cool coincidence. Okay. But it was there once. So that's, anyway. Let's see what's next. Hello. Do lack of normalization, probably multilingual one. Which course today? Hi. Probably same course, but I mean, HuggingFace. Kanishk. Well, that's a really cool name. HuggingFace NLP course. This is the title right here. At the top. I can send. You don't think you understand the L thing, the Arabic L thing? You don't have to. The only thing is that, like saying, for example, alcohol has L, has L at the beginning, because it's coming from the Arabic alcohol. So, okay. And then you say, help me, have something to just have AL in the beginning of a word. Like metal? Metal? No, I don't think so. Anyway, yay! This is just al-alam, which the A and the L, it assumes it's AL at the beginning, but it's not. I'm just saying, like, this has a space, this doesn't. It's just an A, and then it's just an L. That's it. But like that's what I think. Right here, my eye is used to things being, not good. Oh, okay. So if it has a thing like this, it means it's start of sentence. So this is all start of sentence because it has this thing. But we have one case where it's not start of sentence and it's added to this and it's become 7. Don't know if you understand it, but that's how I understand it. Yeah. So we checked the list of frequencies. Yeah. Okay. We can see the ones that are capitalized are start of sentence. And stuff like to is start of sentence, meaning, I mean, that's the whole thing. I keep saying sentence, I mean word, help me, like not within the boundary of a word. Because based on our examples, to see, that's the start. It has a space before it. So this underscore is, oh hi Jess says what's up. This is a space, basically. That's it. Welcome to today's me confusing myself. Okay. Waiting is not fun, and I'm waiting for something, and I keep checking the thing, and that thing is not singing. Okay, so we group the characters with the best subwords to arrive at an initial vocab of the size of 300. So this 300 is arbitrary. We're just saying, let's choose that much. Can I look at them? Dude's terrible at waiting. Thank you, Dude. Yeah. I mean, I don't know if I'm saying this correctly, but you know, patience is a virtue. I've heard that way too many times. I don't know what that means. I just know that patience is a good thing to have. And I am trying to practice that. Yeah, we have a saying that says, patience is bitter, but the fruit of it is sweet. Oh, which is a nice saying. Patience itself is bitter, but the outcome is sweet. Hopefully, not always. Actually, don't expect the word to be nice to you. Space. We have 58 spaces, and then we have 15. This Arabic is doing great. And then we have a tofu. Is that a tofu? Do you guys know about? Oh, thanks. Yeah. Having patience only pays the bill if you are in healthcare. Yeah, they're good at paying bills. Yes. You guys have heard tofu, right? And you've heard of no-to, fonts, which means no tofu. I heard, like, I learned about it while I was a developer, because we would use no-to fonts so that. Oh! Whoa! Hi!
Noir
Who is
underscore
that?
BD just followed. CL welcomes you.
Welcome. Thanks for the follow. Noir? Is that noir? Can't read. Help.
Noir underscore BD just redeemed timeout.
What are we timing out for? Timeout. Okay, I'm waiting. Why do I not have? Oh. Huh? Oh, cool. Huh? Oh, you're on the other side. Got it. Hi. Hi, Ganshik. What's up? Thank you for the follow on the other side, which is the Twitch side. You were on YouTube, and now you're here. That's cool. I like your character. Yeah, I mean, okay, but like, you know, like timeout, it's like in sports, when you say timeout, it's like, okay, why are we time? What for? Like stop. That's what it sounds like to me. Okay, what do we do? I time you out. It's probably a built-in thing. What was I about to say? I was thinking character, but character is not the thing. It's a profile picture. Cool. YouTube is more cool. I can't. Yeah, thanks. Okay. I was thinking you're just testing the waters. Cool. Timeout ended. YouTube is cool because I've been using it before. I mean, I'm kidding, but like it's been in my life, you know, as a thing. But Twitch is cooler for streaming, honestly. YouTube is cool. That's just a fact. But Twitch is cooler when it comes to streaming. I'm sure everybody's heard this, but the only issue is discoverability. I like the fact that now it is split. Cool. Wait a second. Did my eye? Okay, so these are, oh my god. We have Ekthar. We have I was hoping to see لغة, but I can't see it. I just see لغ. لغة means language. أكثر means more. I like this. Oh, لغات, languages. Oh, this is really cool. I was oh wow. Okay, this is really cool. We have al-Arab, and then we have Arabi, and then Arabiya. These all make sense. And here's لغة, اللغة, and then لغة, للغة, for language, I guess. Has less ads during the live stream. Yeah, too many bells and whistles. But for funsies, switch to YouTube in the moment you try to explain the Arabic tokenization and sorry. Okay, I could probably add yeah, I know. You could probably message saying add purgatory or something, because I don't always check the dashboard, Twitch dashboard. Okay. I will stop being fascinated with this split thing in a bit, but before that, the Arabic one is split by character, but Korean, it's split by, I don't know what these are called, but like these are not characters. Tour, and then like moon, like oh no, I can't. Oh, someone wrote in Arabic and I have to read it. Ya Allah. Kunt kara madadi. Oh God, something with a doctor. I can't. المادة فشخ. I don't know what فشخ is supposed to mean. بسبب الدكتورة. Am I supposed to be doctora? Oh God, help. Arabic, not good. Kara, what is kara supposed to mean? Did you list the course number? Did I update the title after stream ends? Yes, and then I put it in the playlist so that if anyone, no, it's not I wouldn't call it a glyph. You know when you read stuff and then you split it by sound, like hello, what is that called? This sort of split. I forgot it in English. Anyway, that's how Korean is written, based on that sort of split. I can't. I mean, I should know. It's an easy thing. Yes, but the thing about the course number, I don't think haven't, like if I say tokenization library like that, I probably could, but because there will be like a bajillion, I don't title them with as much information as I should. Okay. No. Yeah. Now my brain. So like phoneme is a unit of sound, right? Is it supposed to be phoneme? No, phoneme is just a one unit of sound. What's bigger than that? Phoneme. Pair. If I go back, does it make sense for me to say what's a bigger unit of phoneme? Something like that? Syllable. Was it syllable? Syllable. Inferno. Tamam. Water. Yes. Syllable. Yay, we did it. Syllable. It's syllable. Hunger seems to, yep. Blocks of syllables. Yes, you are right. Hunger is written with blocks of syllables, which is actually like intuitive, like makes sense. So yeah, it's split on syllables because it couldn't split them apart, but Arabic can easily be split apart apparently. Because it looks like they are together. You can't split them, but no, you can. But here, anyway, interesting, but sort of out of the. I'm glad that these got split. These are also seem like glyphs, not like. Okay, so I like the fact that it's finding its foot. Do we start training? Sentence Bees uses a more efficient algorithm called enhanced suffix array to create initial vocab. Cool. We compute the sum of all frequencies to convert the frequencies into probabilities. For a model, we will store the logarithms of probabilities because it's more numerically stable to add logarithms than to multiply small numbers. Okay, probably. And this will simplify the computation of the loss of the model. Okay. Like if you ask a computer scientist, why are you using what you're using? They're like, because it looks better. Like I'm using this math because it looks nicer. That is my understanding after trying to learn ML math. I like it to be between 0 and 1, so yeah. Cool. And then I probably can't see the model. Like if I try to look at it, it's probably, ooh, I can. Hey, I thought I couldn't. Cool. I like it. Okay. I thought I would just see the type. All right. Look at you. Okay. You know what? It does look prettier. I'll give you that. Numbers look nicer. Small numbers and limited precision floats probably lose precision quickly. Yeah. Easy to compute is also probably a good reason to use the type of math. I mean, it says so though, doesn't it? It's more stable than it is to multiply small numbers, so it makes sense. The main function is one that tokenizes words using Viterbi. I don't know. Help. Algorithm. As we saw before, that algorithm computes the best segmentation of each substring of the word, which we will store in a variable named best segmentations. We will store one dictionary per position in the word. Okay. From 0 to its total length, with 2 keys. Index, of the start of the last token in the best segmentation, and the score with index of the start of the last token. This is hurting my brain. The start of the last token. Okay, why the last token? Why not just position? Start of position. We will be able to retrieve full segmentation. Start and end? That would make sense. Once the list is completely populated. Populating the list is done with just 2 loops. Okay, so it's a n to the power of 2. The main loop goes over each start position. Second goes to the end. No? Tries all substrings beginning at the start position. All right. If the substring in the vocabulary is in the vocab, we have a new segmentation of the word up until that end, which we compare to what's in best segmentations. Once the main loop is finished, we just start from the end and hop from one start position to the next, recording the tokens as we go until we reach the start of the word. Okay, so this is the encoding. We check for best, and then we probably, if something has a higher score, we update best. Yeah, best score at start. Okay, I'm not gonna go too much into it. If it works, it works. I mean, it's a test. It's not real. Not real code. We can really try our, okay. So we have a model. We have a way to encode, so we can check for probability. What should I check? Probability of words that are outside of its scope, but not too much. So like hopefully fine, but I want to try something else. I'm gonna try something not English, but also, can I make a word out of what's here? Let's try تحديث. Ooh, that works. This is different from yes. Trust me, bro. That's the, there we go. So تحديث would be, we take this ye from here. There we go. Cut. There. Which I think means like renewal. Oh, it's not an unknown. Wow, I like it. That's cool. I like it. Wow. Can I create a Korean word? I don't think I could. Oh. Can I? No. I was thinking the word mother, because we have oh. I can't split those. Oh, okay. No, I can't. Like we have a ma, but it's can I? Let me try. No, I think it'll just go away. Like if I try to, yeah, no, it goes away. Almo. I wanted to make this almoni, but I can't. Like it's almost mother. Oh. I can't. Anyway. Cool. Life is a struggle, and I can't use a Korean keyboard on a laptop. I mean, I could go to Google Translate. Let's go to Google Translate and just get something. Mother. There it is. Now we have omoni. Okay. And this should be a problem because it cannot split on. We should have an unknown. Yeah. Because it can't split, but for Arabic, it's doing better. Yeah. Okay. Compute loss. Ooh, loss is big because. Okay. Score of what? Easy to compute loss on, and we can check. We did. Computing the score of each token is not very hard either, is it? We just have to compute the loss for the model obtained by deleting each token. Correct? Should we? Well. What is that supposed to mean? We didn't have his? LL for hopefully. Removing it will probably make the token L. Make use of the token L twice. We expect it to have a positive loss. Oh. That's a good thing? His is only used inside this, which is tokenized as itself, so we expect it to have 0 loss. A positive loss is a good thing, or meaning it will make the loss bigger. I'm guessing it will make the loss bigger because LL is useful. Oh, it's very inefficient. Yeah, you said so already. Centipede uses an approximation of loss of the model without token X. Instead of starting from scratch, it just replaces token X by its segmentation in the vocab that is left behind. This way, all the scores can be computed at once. Oh, I did not understand it, but the fact that you said it can be done at once, I'm like, yay, good for you. With all of this in place, the last thing we need to add is special tokens used by the model to the vocabulary, then loop until we have pruned enough. Prune is a funny word. Tokens from the vocabulary to reach our desired size. So we just take stuff away. And like here, we're saying 100 is enough. I think we had 300 last time. Oh, wait. Huh? Sorted score. Where are you coming from? Out of range. How? Size? How's the size? Oh, I expected you to print this. Print something? Whoa. Whoa. Percent remove is 0.1. And the error was here. I and 0. That's weird. Oh, okay. That makes sense. You're having a hard time with finding? Okay. That's sad. Don't know if it's my fault. Probably is for using stuff that I'm not supposed to use, but anyway. Tokenize some text, just need to apply pre-tokenization and encode. Okay, so right now my model size is the same, I'm guessing. I don't think I removed anything. Yeah, because here pop is supposed to remove it, right? Alright. So now this is just English. This is doing this is the only thing that it has recognized. Is it the same here? No. Did I remove a sentence? Huh. That's it for unigrams. Yay! Hopefully by now you're feeling like an expert in all things tokenizer. I'd say I'm more confused, but thank you. In the next section, we will delve into building blocks of the tokenizer library and show you how you can use them to build your own tokenizer. Inshallah, inshallah. I would like that. I wanted to test another word. So what we did is word with offset and then pre-tokenized, so they're not tokenized, and then we encode them and then give them. Oh. And then we just return the encoding? And isn't that basically a tokenizer? But we're using a pre-tokenize from the tokenizer. Let's tokenize another word/sentence that is not in English. We have Arabic, Japanese, and Korean in our vocabulary. I can't Japanese, but I should Arabic. Let's try something Arabic. So let's try, hello, my name is CL, which I would apologize. Aw, that's cute. Let's go with, how are you? And then my name is CL. So that, why didn't Google Translate right? Oh, where's my punctuation? Google Translate did not write punctuation. Anyway, so marhaba, and then this is English. Oh well. Nope, not English punctuation. I'm not gonna accept it. If I let's my name is cool. Because it SL works. Marhaba, give me a this. That's not Arabic, is it? Wait. I don't think it is. Okay, this is it. Okay. And a dot. Oh, that's not a dot. Oh, this is a dot. Cool. Hey, that worked actually. It became CL. Let's replace that. Whoosh. There. And paste. And run. Oh, we have an unknown. Which is question mark, obviously. That's cool. Right? We have cave. Marhaba, cave. I guess halik is, where's L? Where's L? Here it is. Okay. Wait, what happened? Oh, because of this, this whole thing became unknown because of the question mark. If I update the question mark to I update the question mark to, okay, English. I don't think it will help because it's not expecting punctuation, right? Okay. Nope, it's not expecting it, but it did accept you. Same? Okay, so whatever that was in our vocab, which dot was available, but question mark wasn't. Cool. And now hal. Okay, halik. If it's, yeah, it's here. Nice. We did it. I have about 15 more minutes. I'm not gonna start something new here. Building a tokenizer. Whoa, look at us. Yeah. This is our last thing before the quiz. This check is mostly just a review. I thought I'd never get here. This is probably going to be I don't know, at least a full day thing. But hey, I am proud of myself for not giving up because I'm good at that. Let's try a very brief, probably less than 10 minutes of lecture. Maybe we'll stop at this part. Yeah, I will see. So I'm gonna go back just a bit. Have CC on.
So the other option that you can use is don't tune all of the parameters of the model, but just some of them.
Mm-hmm.
And this is really popular nowadays because
This lecture is supposed to be about fine-tuning and instruction tuning.
this further improves your ability to train on many different, data sets without huge GPUs or without many GPU devices. And so the first one is something like prefix tuning. So I already talked about this last time. Prefix tuning is like a bridge between parameter efficient fine tuning and prompting, right? So it tunes one prefix for each of the layers. So the next one that I'd like to talk about is
Okay, this is a reminder. Okay.
one. So the next one that I'd like to talk about is adapters. And adapters basically look like this. So what you do is you have your standard transformer architecture,
Mm-hmm.
which has, like multi-headed attention, and other things like this. And yeah, this is written in a slightly different way than I wrote the transformer diagram, but it's saying the same thing. So multi-headed attention, this is kind of your your Q, K, and V matrices. And then this is your O matrix.
I mean, I should probably review QKV, but at least I know that I've heard it before, even if I don't remember well.
And in the transformer architecture. So this is what we were calling multi-head attention in the previous diagram.
Mm-hmm.
This says 2x feed forward layer. It's basically 2x linear layer with a sandwiched nonlinearity. So it's basically a feed forward block. So this is just the standard like transformer. So what adapters do is they add yet another layer right here. And you freeze the things that are in gray here, like the feed forward layer, multi-headed attention, but only train this adapter. And the way the adapter works is you have a standard large representation vector here, and you have a feed forward down projection that down projects to a very small number of nodes here. And then you have a nonlinearity, and then you have a feed forward up projection that projects it back to the standard space. And this is included within the residual layer here. And so ideally, this will project down from like 512 to something like 16. And then back up to 512. So if it was just a 512 by 512 matrix, that would be 2 to the 9, right? So you get 2 to the 10 parameters. Right.
His voice is a bit far.
Yeah, 2 to the 10. 2 to the, right? Yeah, 2 to the 18 parameters. This is only 2 to the 4. So if you have this, that would be 2 to the 9 plus 4 plus 1 is 2 to the 4. So you would have 16 times less parameters for the adapters than you would have for the...
I think the subtitles are helping because they're pretty accurate.
For the full matrix. So, and then if we, instead of using 16, we just did 2 or 1 or something like that, it would be, much less. So basically, by making these matrices or these vectors very skinny, this allows us to minimize our minimize the addition of parameters.
I think this is the same thing he said yesterday. 3243. Okay. Like this making it skinny like this. Anyway, 3243. That's where I was. Yeah.
Minimize the addition of parameters.
Okay.
So are there any questions about this? Yeah. Yeah, so why do they make it smaller and then larger? The main reason why they make it smaller and then larger is because that's a way to reduce the parameter count. So if they kept it the same size, it would be 2 to the 18, but you would actually have 2 of them.
I mean, did I do probability stats, linear algebra before studying these concepts? I did linear algebra and statistics during my bachelor's, which was 10 years ago. Like 9-10 years ago. Based on which level I was in, and which one I was studying. So yeah, I did. But that doesn't mean my brain is in shipshape. Yeah. Yes. Okay.
You would have 2 of them, so you'd have even more parameters. But so it would hurt the performance. So making them smaller would hurt the performance if you had lots and lots of training data. So if you have lots and lots of training data, you would benefit by making the adapter dimension larger and just fitting very well. But if you have lots and lots of training data and you have the memory that allows you to train a larger model, then you might as well just train the whole model itself. You might as well do full fine-tuning. There's 2 advantages to parameter efficient fine-tuning methods. The first one is that they reduce memory, like I mentioned here, reduce the memory for the parameters you're training.
Okay.
Also, because there's fewer parameters, it's harder to overfit. So if you have very small training data, full fine-tuning can overfit and become unstable. But because this has fewer parameters.
Okay, but come on. Like you can reverse what you said and just say this has fewer parameters, so it's not going to be good. The other one has more parameters. It's probably doing better. And obviously overfitting is an issue, but everything is a problem and nothing is a problem at the same time.
Parameters, it essentially is less easy to overfit and will generalize better often. Yeah. So when you fine-tune, you only fine-tune the parameters of the adapters. And so we assume that we have a pre-trained model, like the gray parts are pre-trained, and then we fine-tune just that.
I have a question. I thought less parameters overfit more quickly. I don't know. I don't know. But I was thinking, sometimes when we use the same model to do different tasks, we use different heads. Does it make sense to fine-tune heads? Is that an option? Like I need to go in less than 5 minutes, so let's see where this conversation goes.
So, very good question. You need to. So the question was, even though we are only fine-tuning the adapter layers, we still need to store the gradients of the other layers, right? So we still need to store this part. That's actually not the case. So when you are doing backprop, you only need to do backprop into the parts of the model that are on the path to the gradients that you want to be updating. So like, for example, if I write...
How long is this answer to this question?
If I write the computation graph...
No, I can't. Okay, 2 minutes. Fine, I will. Thank you. He's being quiet. Pali. Hurry up. 뭐야? Say something. Oh wow, he's not talking. Okay, did he
So
talk?
this is like a computation graph of an attention block. So we get our loss, like the gradient from the loss is flowing in here. And so it goes back to the feed forward network, to the adapter, to the attention, and then here. So we definitely need to pass it back through the layers so we get to, like the earlier layers and stuff. We don't actually need to pass it into this, into the weights of the attention, because we're not updating them, so we don't really need to even calculate the gradients of the weights of the attention. We also don't need to calculate.
The board is not being recorded well, but I will thank the fact that he put it online, and I could probably use a better resolution. But also thank the fact that he's using a wide lens. So
The gradient of this.
I'm not complaining that much.
But we do need to calculate the gradient of this because we're updating it. So basically, you don't even need to do backprop into parts that you can just cut off without updating. Yeah. For forward, you do need to, use them obviously to calculate the forward pass. So by being smart about that, you can fix that. There's also something called checkpointing, like computation graph checkpointing, or forward pass or backward pass checkpointing, where basically what you do is you calculate part of the way through the graph and then throw out the intermediate calculation. And so, for example, you might do the forward pass all the way up to here, and then throw out all the intermediate states, and then recalculate them when you're doing the backward pass. And so there's lots of tricky things that you can do to squeeze your memory if you need to. Yeah.
Okay, I'm gonna stop here. Yes. You can do a lot of stuff if you have time on your hands. Cool. Tweak a lot of stuff. Okay, thank you. Thank you, all the lovely people, for being here. I appreciate the conversation. Thanks, Kanishk, I think, for the follow on the I think on both sides. I don't know. But yeah, I had fun today. I like learning. Oh, 뭐야.
Our MTW just followed. CL welcomes you.
Yes, you are being welcomed, but hold up. IMG. Oh, it actually read it correctly. That's cool. IMG. Oh, cool. Thank you for the follow. I appreciate it. Did not expect that at last minute. Lucy Dust. That's a cool name. All right. Inshallah, I shall be coming back tomorrow if all goes well. Tomorrow is 환영합니다. It's supposed to be 안녕하세요. 어머. 와. 환영합니다 is welcome in Korean. follow는 그냥 follow 아니에요? follow 해줘서 감사합니다. Thanks for the follow. 네. 지금은 네. 오케이. 가야 돼. 미안해. I have to go. And why did I speak in 반말? What's wrong with me? 미안해요. 반말 is like a, it's not disrespectful, it's just speaking to your friend. 우리 친구야? 미안. Okay, that's it. I'm not gonna embarrass myself more. 감사합니다. Yes. Good. Please do study. And then we will study again, inshallah, tomorrow. I think I will have time. This week I should have time. Last week I didn't. But inshallah this week I will. So 다음에 또 봐요. 내일? Maybe tomorrow. 네. 감사합니다. That's it. Thank you. Good. Bye. 네. I will count down from 5 and then I will go. There are links around. I don't know if you want to be on Discord. It's super quiet. I like it to keep it quiet unless something important is around. So I will not bother people. I'll do my best not to bother people. Okay, 이제 갑니다. Starting from 5. I will be ending the stream in 5, 4, 3, 2, 1. Thank you so much and see you tomorrow, inshallah. Goodbye. 안녕.